Thank you. So, hello. My name is Ohad. I'm a master's student at the McMars group, a quantum computing and machine learning group at Bar-Ilan. And I'm going to talk about this. So we will start with a short introduction, which I'm sure many of you are familiar with, but I'll do it anyway. So about a decade ago, the state of matters in the quantum computing community was pretty much we had some working devices, some small and noisy working devices of several technologies, but we didn't have suitable algorithms to execute upon them. We had Shor's algorithm, we had phase estimation, we have even today the same situation, but it is very far away from the real devices that we have in terms of capabilities. So what we did is start to think and research in the direction of what we can do with what we have. And this is how hybrid algorithms and variational algorithms were born. And the idea of a hybrid algorithm is pretty simple. You take a problem, you take the classical intractable part, you encode it into some quantum form, and you craft an ansatz, a quantum circuit with the parameters within it. You formalize a suitable objective function to optimize that depends on the parameters of the ansatz. And then you iteratively execute this ansatz multiple times, measure, push the results into the objective function, and optimize the parameters. And it's not a magic. It's not that we have transformed phase estimation into a shallow VQE circuit and we have solved all the problems in the world. But the really state of matter is that even today we have not a single case of a demonstration of a real advantage that we have gained with this approach. And even we have discovered many problems of VQAs and hybrid algorithms that are discussed in the literature, such as Brownian plateaus, large amounts of measurements and shots that are required to gain signals, etc. And it seems that even if we put these problems aside, it seems that even today, the hardware is still too noisy, and you need to do something really sophisticated and spatial to compete even in the field. So this is what I'm going to talk about. I'm not going to talk about a single paper. I'm going to give sort of a bird's eye view on the activity of the group in Bar-Ilan, which I'm a member of. And our activity is around this question. Can we craft sophisticated lean, and by lean I mean shallow and narrow algorithms to achieve useful quantum computation as fast as possible with the hardware that we have. So I'm going to briefly, really quick, go over these three papers. The first one is about quantum chemistry. The second one is presenting an approach to address ansatzes on the pulse level rather than on the gate level. And the third one is about quantum optimization. And in each paper that I will present briefly, there is a novel approach to how to do this stuff in simple words. And there is a theoretical building of the algorithm followed by some experimental simulations and real quantum hardware results. All algorithms are heuristic, and I'm going to talk about it. It turned out that when you optimize something, you lose somewhere else. And this is the delicate spot that I will speak of. So the first one is a qubit-efficient variational selected configuration interaction method, VQSCI in short. And the goal of this algorithm is approximating ground state energies of molecules. And the way it works is simply as follows. By classical methods, you select only the most dominant electronic structure configurations of a molecule. You map these slated determinants, which are configurations essentially, into computational basis states. in contrast to VQE, where you map each spin orbital to a qubit, here the single qubit state has no meaning. Each computational basis state is mapped to a full configuration. And after you do that, you look for the ground state in pretty much as in VQE. And you can see the scaling here on the left in terms of qubit consumptions, and on the right in terms of required measurements, the decomposition of the Hamiltonian to Pauli strings. And in green, it is this algorithm, VQSEI. In red, it's VQE with the standard Jordan-Wigner mapping. And you can see that the scaling is much better in this algorithm in terms of qubit consumption when you scale with the number of electrons and spin orbitals. But you lose, as I said before, no free lunches, and you lose here. In the beginning, we are better than VQE, but when you scale enough, you start to lose, and the number of Pauli strings you need to measure is becoming large. Here are some experimental results. If you needed to focus on something, so look on the purple triangles compared to the light blue X's, which the purple triangles are the noisy simulations results for VQSEI compared to the X's, light blue X's, which are VQE noisy simulations. And you can see that consistently we get better results. The real hardware results are in red, and they reach chemical accuracy in hydrogen molecule, and they are not better in the more large molecules. So to conclude with this algorithm, it seems that although the approach is novel, the time advantage with this algorithm seems unlikely due to the measurement scaling. But we can think of a possible memory advantage, and it's a real bottleneck from computational chemistry with these numbers. And that could happen, we think, if you could generate the configuration interaction matrix on the fly, and this is something we work and research upon. So moving on to algorithm number 2, it is called determination of molecular ground state via short square pulses of superconducting qubits, and it's a little bit misleading, this name, because it's not specifically about this, and it's not necessarily about approximating ground state energies of molecules. It is about addressing ansatz directly in the pulse level rather than in the gate level. In this paper, we did it for this application, for chemistry application, but you can do it for whatever ansatz you wish. And the idea that we employed is optimizing the amplitudes of as short as possible square pulses time bins, as you can see here. Each time bin is dt. And with the hardware that we worked with in this paper, it was 0.22 nanoseconds. And here you can see some real hardware results for the hydrogen molecule, where in the pulses appear in blue and gates appear in red, and you can see it is better, and we even reached chemical accuracy in some conditions. And what is really interesting here is that we managed to achieve chemical accuracy with a really, really short pulse of 0.22 nanoseconds, just one discrete time bin. A little bit of excitation comparable to a slight RY rotation, if we think gate level wise, was enough. And it is compared to the minimum implementation of, with this hardware, 70 nanoseconds RY rotation, or it can be other quantity with different hardware, but it's going to be much order of magnitude larger than this quantity. Here on the right, you can see classical simulation of lithium hydride, and I think it's interesting to see the unusual shapes of pulses that you get here. And we are not limiting ourselves with this approach to a Gaussian pulse or a drag pulse. We let the optimization process do what it has to do. And so to conclude this one, it seems that the approach and results looks promising. And indeed, improvement by orders of magnitude in circuit depth or computation length seems very handy when dealing with noisy hardware. And it is very logical to me that the gate level abstraction might be redundant when you work with hardware efficient ansatz. You need the gates to do some computation you mean to do, but if you let the optimizer optimize angles within a black box for you, so you probably don't need the gates which are more strict, and you also need to calibrate them. You can also think of that overhead that you can spare. And I will proceed. So the third and last algorithm is qubit efficient max cut algorithm, QENC in short. And it is about approximating max cut of graphs. And the way it works, so we map pretty similar to the quantum walks mapping that was shown before. We map each graph node to a computational basis state. So if you have graph with V nodes, you need just log V qubits to encode the graph problem into the quantum circuit. And the way we encode the cuts is by binary partitions of the probability distributions that we reconstruct from measuring the ansatz, which is heuristic, multiple times. I will explain with this toy example. We have a graph with 4 nodes. Each node is mapped to a probability from 0 to 3. And we heuristically assume that the number of blue nodes in the graph is 2, where we try to divide the graph into blue and white subsets. So we set the threshold, the probability threshold to 1 over the 2b, which is 1 over 4 in this case. And we take all the probability nodes that above this to be blue and the others to be white. And it is required to say that we are treating the quantum computer as a computational black box that operates in large space with entanglement and such. And we act uniquely on the probability distribution while applying this objective function. What this objective function is doing is it's driving the probabilities of adjacent nodes away from each other. So if we take the example from before, where b equals 2, so we want the absolute difference and sum to equal 1/2 exactly, and then this whole thing is zeroizes, and of course it's always positive because of these powers. I will go over it briefly because of the time. So these are experimental results for small graphs, where in green, the green line is the optimal max cut. This is classical simulation. This is real hardware. And of course, you can see a degradation in results due to noise. But when you compare it to QEOA, and we did it pretty straightforward, we took graph instances from a Google paper, which benchmarked it with QEOA, you get the results which are 1-2 orders of magnitude better. And these are results for with classical simulations compared to the classical Gormans and Williamson algorithm, which is the baseline here. And you see that you get better results for graphs with nodes up to 2048. Do I have more time? No? 1 minute. Okay, so I will go here. So to conclude all of these algorithms and approaches, we have shown 3 algorithms, each with, I think, unique approach. And in every algorithm, we saw that you gain something, you lose somewhere else. But it also, I think, interesting to say that in every algorithm, we did not encode any structure into the quantum part. We kept the quantum part as lean as possible to avoid noise, but we gave up on problem structure to be encoded into the quantum part for this. And I think if we look forward into the near future of quantum applications, I think we are going to pay close attention to this sweet spot intersection. I think that structure is is unavoidably going to be encoded into quantum circuits, even if in hybrid algorithms, even at the cost of circuit depth. But it is very delicate. You can play with depth and structure and possibly find something here. Thank you. Yes, you in the free pulse optimization paper, this specific implementation was based on the first algorithm that I've shown, the VQSCI. So you took the molecules, you mapped them to Hamiltonian using the SCI classical method. And then instead of looking for the ground state with gate-based ansatz, you looked for the ground state with pulse-based ansatz. So you chose heuristically a number of time bins, I would say 5. So you have, I'll show it here. So you have horizontally 5 time bins to optimize, and on the vertical axis you have control channels. This is drive of the first qubit, this is drive of the second qubit, this is the 2 qubit channel. And you apply pulses on these channels where the parameters to optimize of the ansatz is the amplitudes of these squares.
Okay, and basically the y-axis is either channels or pairs of channels? Or
yes, exactly, yes. And what's interesting about it, I think, is even if you intend to play a Gaussian, I would say, on a standard quantum computer, so it is, in the most fundamental way, it is composed of these tiny square pulses. So you just let the optimization process figure out whatever pulse shape it is better for the optimization process.
So at the end of this process, you still have to somehow get the energy out of it?
Yeah, you measure. You perform measurement regularly. This is just the unitary evolution.
If not, then let's thank God again.